Okay, so for this evening, I was thinking of reviewing homework assignment number 5 and number 6 because much of that material is going to wind up obviously on the upcoming exam. And I think it might be a good time to maybe kind of give you guys a little bit of an advantage on that. Not gonna use exactly the same numbers. I'll probably change a few numbers here and there so you can see the techniques without giving away the farm, so to speak. Okay, so I'm gonna open up the. I'm gonna use this version of it. Let's see if I can't find it. Okay, I have a version of it here. It may differ from class to class, but I think for the most part, it's pretty much the same. So let me see if I can't go in here and find it easily. Okay, and I'm going to go into assignment number 5 and assignment number 6. Actually, there's two parts of number 6, 6 and 6B. Actually, I'm going to do 6 and 6B. I think that I'll do with that, and maybe on Sunday evening when I do another session, that will take. I can step back a little further if people are still uncomfortable with that. So let's take a look at assignment number 6. Okay, I'm gonna work on this as if I'm doing it just like you are doing it. Okay, I'm gonna make this screen a bit bigger so we can read it a bit. Okay, so let's see. You wish to test whether the number of fouls called in regular season games is different than during the NCAA tournament. I guess first probably this question up in March when the finals were going on. The mean number of fouls called during a regular season game is 40.1. Notice I use mu for that. In other words, they tracked all the regular season games. We have the entire population of regular season games, and the mean number of fouls happened to be 40.1. During 16 randomly selected playoff games, we have a sample here. So we have a known mean that we're comparing to a sample mean. Okay, the mean we sampled 16 games, and the mean number of fouls during those 16 games is 38.1, and the standard deviation for this sample for those 16 games, the standard deviation was 5.8. Okay, so now you want to calculate a 95% confidence interval. The first part of this problem. You want to calculate a 95% confidence interval for the mean number of fouls called during playoff games. Okay, I'm going to change these numbers a little bit. I'm going to stick with the size 16. I'm going to change the mean number of fouls to 39 and the standard deviation to 5. Okay, just a little bit different. Okay, I'm going to open up Excel because I think it's time we learn to get comfortable with Excel, and also it'll speed up the calculations and make it a little easier for you guys to avoid making a mistake. I'll open it up. I'm going to make the cells quite a bit bigger. Okay, blow them up, and I'm going to move this down here so we can read that at the same time. So I'm going to say, okay, what do I know? I know X bar. I'm calling X bar. I forget what I said I was going to call it. Instead of 38.1, I'm going to call it 36. Okay, and the standard deviation, right? The standard deviation S or SD is from the sample. I don't know the population standard deviation, or at least I haven't been told what it is yet. Okay, sample standard deviation was 5.8. I'm going to call it 5 for our purposes. And our sample size, I'm going to leave that at 16. Okay, so we're asked to calculate a 95% confidence interval for the true mean, mu, the true mean of the number of fouls called for all of the playoff games from a sample of 16 playoff games. Well, because there's 32 teams in March and they all play each other. Boy, they play hundreds of games, I would think, right? If we figured it out, right? So there's a sample of 16 from there. We're not interested. We don't care what the mean of the sample is. The only reason we calculate the mean of the sample is because it gives us a clue. It approximates the mean of the population. Hi, how you doing? Good. I have an audience now. Okay, we have, besides somebody online, we have an audience in person too. Okay, so what I'm doing, just to back up, what I'm doing is I'm going over homework 6, which is the sample hypothesis testing, the single sample t-test, and the multiple sample t-test, like the independent samples t-test, 2 samples, paired samples, and so on. So I'm going over the homework. I'm changing the numbers a bit, so I'm not giving away the farm. I'm recording it also. So we'll go through that, and then we'll also give it a try later on, I think. Yeah, on Sunday night, I'm going to do another session so that anything that we don't get to now, we'll get to then. Okay? It's hard? Not that hard. Okay. Yeah. Okay, so at any rate, we take a sample, size 16. The mean for that sample is 36. The standard deviation of the sample is 5. What we're really interested in is determining what the mean of the population, the mean of all the games is, right? So, but we're never going to know that unless we actually measure all the games. So the closest we're going to get is what our sample mean was. But now we want to know how accurate that sample mean is. What range of numbers do I have to have in order to, what lower limit, upper limit do I have to have in order to be 95% certain that I actually know that the true mean is within that range? Okay, we're going to calculate a confidence interval. We've done this a few times before. This is kind of an introduction. So the way we calculate it is x bar plus or minus, okay, and we're going to apply a score here, a z-score or a t-score, right? The number of standard deviations apart, or number of standard errors apart that you need to capture 95% of the samples from a population, given a sample size of 16. So that's either going to be a z-score or a t-score. Okay, now before I go any further, let's decide which one we're going to use. If I don't know the population mean, and I only know if I don't know the population standard deviation sigma, but I do know the standard deviation for the sample S, should I use the z-score or the t-score? If I don't know the population sigma, I should use the t-score. If I know sigma, the population standard deviation, I can use the z-score instead. So I need to use t, whatever the value of t is. Well, what determines the value of t? The thing that determines the value of t is the sample size. We go to that table and we look up for that sample size, that number of degrees of freedom, what number we should use for t, for 95% in this case. Okay, and we're going to multiply that times the standard error. Times the standard error. Okay, so now, okay, so we need x bar, we have, t we're going to look up, and the standard error we need to calculate. How do we calculate standard error? Well, the standard error is equal to sigma over this square root of the sample size, right? So sigma over the square root of the sample size. So I don't know what sigma is. So since I don't know what sigma is, I have to use S, the standard deviation for the sample. Again, another reason why I have to use the t-score. Okay, so if I calculate that, equals, okay, the standard deviation is 5 divided by the square root of 16. Okay, that gives us a standard error of 1.25. So now I'm going to go back here to my x bar plus or minus t times the standard error. And now I need to know what t is. Okay, so we know what standard error is. Whoops. Okay, now I have to know what the t value is. Well, in order to know what the t value is, I have to use my table. Okay, I'm going to dig up the table. Yeah, actually came right up. Okay, t table. Okay, so where to go? Is that it? There it is. Okay, we got it. Some extraneous stuff there too, whatever I opened it up before. Okay, so let's take a look at this. For our degrees of freedom, it was the sample size was 16, so that's 15 degrees of freedom. For 15 degrees of freedom, we use the t value. Let's see, 95% confidence is going to be this middle column here. So for 15 degrees of freedom, in other words, a sample size of 16, we use a t-score 2.131. So t is equal to 2.131. Now, had we known what sigma was, instead of having to get it from the sample, we could have used 1.96, right, the z value. But we use the t-score because it's a small sample size and we don't know what sigma. The problem didn't give us what sigma is. Okay, so let's calculate this. So our confidence interval is equal to x bar. So x bar is 36, right? That we were given that. Okay, plus or minus, and I'm going to calculate what that plus or minus is. That's called the margin of error, right? So I'm going to calculate, that's going to be equal to our t-score. It's going to equal our t-score times our standard error. And that comes out to that number. Okay, so x bar plus or minus that margin of error is going to be equal to, it's going to be equal to 36 minus this number, and 36 is going to be equal to 36 plus this number, that margin of error. So we're 95% certain that the true mean for the population that this sample of 16 values was drawn from, the true mean is between 33.3 and 38.6. It's between those two numbers. Okay, just to quickly go through the steps for you guys that just turned up here or online. Okay, we were given, I remember now, this is from the homework, but I changed the numbers a bit, right? So when you go back through the homework, you can emulate what I just did now, except use the actual numbers in the homework. Okay, so we want to test whether the number of foul balls during the regular season game is different than during the tournament. The mean number of foul balls during regular season, mu, is equal to 40.1. We're told that for the regular season. We know what mu is, right? But for the playoff games, we only had a sample of 16 games. And during those 16 games, the mean number of fouls was 38.1, and the standard deviation was 5.8. I changed those numbers a little bit, I think, to 36 and to 5. And we were asked to calculate a 95% confidence interval. And the way that I did that was, again, I said, I know the mean, I know the standard deviation of the sample, not sigma, not the standard deviation of the population, but only of the sample. I know the sample size. So I calculate my standard error, which is equal to the standard deviation, sigma if we know it. Excuse me. So thank you. Sigma if we know it, right? In this case, we don't, so we use the standard deviation of the sample divided by the square root of the sample size, which is I think it was 5 divided by the square root of 16, and that turns out to be 1.25. Now, my calculation of confidence interval is always the point estimate, x bar or p cap, whichever it is, x bar plus or minus the t or z value. If we know sigma, we can use z. 1.96 for 95%, 2.58 for 99%, 1.64 for 90%, right? Confidence interval. Usually we're doing 95 most of the time. But I can use that if I know sigma or if the sample size is very large, right? That's neither is the case here. So I have to use the t-score. And I got the t-score again by looking it up on the table, right? And the t-score is based on the confidence that we want, 95%, so it's in this column, and the sample size. Except that in this case, we use degrees of freedom instead of sample size, and that's just equal to the sample size minus 1, 15. So the t-score that we need is 2.131. So I used that. So I calculated x bar, which was 36, plus or minus the t-score, 2.131 times 1.25, and we got 33.33. Then I repeated that. X bar, 36, plus t times 2.131 times 1.25, added to that, and I got 38.66. Okay, simple as that. That's all we had to do for that problem. That's all they asked us for was a confidence interval. Okay, again, the answer in the homework is a little bit different. Yeah, issue, this problem? Mu represents the mean for the entire population, all the games. X bar represents the sample mean. In other words, when I said mu, that was the mean for all of the games during the regular season. In other words, they had the scores for every game during the regular season. X bar represented the 16 games that they had during the playoff, NCAA tournament, right? They didn't have all the games. Probably is 100 games, right? 32 teams and the two brackets, and they play forever, right? That all of the games might be 100 games or more than 100 games. They only actually sampled 16 randomly, so we didn't know all of the games. All we knew was that sample. So we wanted a confidence interval for the mean for the playoff games. In other words, if I took all the playoff games, what would be the average mu for the playoff games? We don't know what it is, but we do know what X bar is, and we can calculate a confidence interval. Okay, continuing the problem above. You calculate a 95% confidence interval for the mean number of fouls played during a playoff game. The upper level, you fill that in there. The lower level is another number we calculated. We filled it in there. Using the data above, you wish to perform a hypothesis test comparing the mean number of fouls during a regular season game and during the playoffs. Your null hypothesis. We got to make a null hypothesis. We want to know if the average number of fouls called during the regular season is the same as the average number of fouls called during the playoffs, during the tournament, right? So, what's a good null hypothesis for us? What do you think? What does it always start off with? We always start off with the equality, right? The mean number of games, the mean for the number of fouls during the playoff games is equal to the mean number of fouls during the regular season. It happens in this case, we know the mean for the regular season, right? Okay, we were told that. We don't know what it is. We only know the sample for the playoff games, right? So our null hypothesis is going to be mean for the regular season is equal to the mean mu for the playoff games. Using the data above, you wish to perform a hypothesis test comparing number of fouls. What's your alternative hypothesis? Well, if the null hypothesis is that we think they're equal, our alternative hypothesis is that they're different, right? That they're not equal. So it would be mu regular season does not equal mu for the playoffs. Mean for the regular season doesn't equal the mean for the playoffs. So our job now, the next, if you want to drop the other shoe, as they say, right? Our job now is going to be to see if we have enough evidence to reject the null hypothesis that they're equal and accept the alternative hypothesis that the refs are calling more or fewer fouls during the playoff games, right? So that's our job is going to be to try and see if we have enough evidence to throw out the null hypothesis, reject it, and accept the alternative hypothesis that we caught the refs changing the way they judge the games, right? So that's really what we're after here. Okay, so using the data above, what's the critical value of t you would need to exceed to reject the null hypothesis with alpha error equals 0.05? In other words, with 5% chance of being wrong. Okay, so how do we decide what the critical value of t is going to be in order to reject the null hypothesis at that level of acceptable error? Remember before, what did we use for the confidence interval before? The t-score, right? And it was based on the t-score for that sample size. So the sample size, there's only one sample. One thing is known, the mean for the regular season is known. The mean for the mean for the playoffs is not known. You just know the sample. So we're going to calculate our t-score. How many t values apart these two values are. The mean that we know and X bar, right? X bar minus the mean for the regular season. So we're going to calculate that. But what is our critical value of t? How far apart do they have to be, right? Well, we go back to our table, and it was just like calculating the confidence interval. What was this? What was the sample size again? 16, 15 degrees of freedom. So our t-score has to say that those two means, the sample mean and the population mean, have to be at least t-scores of 2.131 t-values apart, t-scores apart. Okay, and we're going to calculate that in a moment. So the critical value is 2.131, just like it was for the confidence interval. Okay, given that, what is the value of t that is associated with the difference between the regular season mean and the sample mean? Okay, let's calculate that. Yes?
It would also include the standard error, basically.
The standard error is how much the actual number you add and subtract from the mean to get the 95% confidence interval. The t-score, the critical value of t, is how big t has to be in order for you to reject the null hypothesis. We're going to calculate it right now.
It's always the t-score.
Right. Yeah. Critical value, we're usually talking about the t-score. Later on, we're going to be talking about chi-square. We'll talk about what's the critical value for chi-square. And we're talking about analysis of variance. What's the critical value for that statistic? In other words, what do we have to exceed in order to reject the null hypothesis? So how do we calculate t? Well, calculate t the same way we calculated z when we were dealing with populations, right? T is equal to, just like z, is equal to, what's it going to be equal to? It's going to be equal to x bar minus mu, the difference between the two means. In this case, one of the means is a sample, right? Just the difference between the two of them, divided by the standard error, right? And the standard error we know is really, what is that really? That t is equal to x bar minus mu, the difference between the two means, divided by the standard deviation over the square root of the sample size. Okay, I'm going to put all that in parentheses there so we keep it separated. That's what we're going to do. That's the standard error on the bottom, and that's t on top. So let's work that out. Okay, I'm going to do that over here. I'm going to say t. Okay, and over here I'm going to I'm going to find out what the difference on top. Now, my recollection was that x bar was, I think I called it 36. Remember, it's not the same as a problem. I changed the number. 36 minus, and the mean for the sample was 40.1, right? 40.1, right? And that's going to be, okay, I'll leave that up there. And that's going to be divided by the standard error. And that's equal to the standard deviation, which I said was 5, divided by the square root of the sample size, which was 16. Okay, and that comes out to 1.25. So what's our t-score going to be? Our t-score is going to be equal to negative 4.1 divided by 1.25, okay, which comes out to a t-score of 3.28. It's 3.28 standard deviations apart, these two standard errors apart, these two values, right? What did we say the critical value of t had to be? You got exactly right. The critical value of t critical from the table, was equal to 2.131 for a sample size of 16. We have to have these two things, the x bar and mu, have to be far enough apart that they are more than 2.131 standard deviation, standard errors of the sample means, apart in order for us to reject the null hypothesis. Can we reject the null hypothesis? Is our t-score bigger than 2.131? Remember, so that it gets smaller or bigger. It doesn't matter because we didn't care whether one. We just said how to be different, right? So it is. So yes, we reject our null hypothesis and we accept our alternative hypothesis. Okay, that's it. Most of these problems, most of the problems are going to get a little bit more complicated because they're going to use more than one sample. But stepping through this, and you guys that got here a little later, that it's recorded, so like you'll be able to. Basically, what I'm doing is I'm taking homework assignment 6 and 6B, and I'm going through the problem. I'm going to go through these problems now, and I'll also go through the ones we don't go through now on Sunday night. Have another session online, and it should help you with this homework. Okay, I changed the numbers a little bit, so you'll have to do it on your own, but use the numbers in homework. You can follow the same thing I did, except with the actual homework numbers. Okay, so I think you should be able to work that out. Okay, so let's take a look at where we wound up then. Okay, so value of t, but the difference. Okay, using based on can you reject the null hypothesis? Okay, over here, you first of all reject the alternative hypothesis. We never say that, right? The only thing we ever say is accept the null hypothesis, or, excuse me, you don't say that either. We say reject the null hypothesis and accept the alternative hypothesis, or we say fail to reject the null hypothesis. That's not one of the choices, right? So the right answer here is in the case of the numbers that we got, right? I say reject the null hypothesis and accept the alternative hypothesis. As they say, your mileage may vary, right? I don't know if you really worked it out. I don't know if you would get your t-score bigger than t-critical. I say, look, from the looks of the numbers, I think you probably would. So you might get the same answer. Okay, so you guys okay with that? Make some sort of basic sense. Like I said, you can always play this back, go through it slowly, and as you're playing it back, use the actual homework problem. Because I have it turned on so it will tell you if you got the answer right, so you'll know, whether you got the answer. And as always, you can always go back and do the homework again. Okay, so let's see. The average FEV, you guys are nurses, you know the FEV, forced expiratory volume. That's the amount of air that you can blow out in like 1 second, right? That's FEV. FEV1 is the amount of air you can expel in 1 second. For a normal person, that's like, I don't know, I think 2 or 3 liters or something like that, right? And maybe it's less. Maybe that's the total volume. I don't remember. It's been a while since I actually had a pulmonary function test. But at any rate, FEV1 is how much you can blow out, and they use that test to diagnose chronic pulmonary obstructive disease, right? So it's a commonly used test. So the average FEV volume for adult males 20 to 49 years old is known to be 3 liters. They just gave you mu for the entire population. That's all adult males, right? Has an average of 3.0. You know what mu is. Rare situation, usually you don't, but for this problem, you know what it is. You randomly sampled 60 male construction workers. Now, this is not the general population. This is specifically construction workers. You randomly sample 60 male construction workers exposed to high levels of construction dust in the same age as those men there. You wish to determine if the FEV for construction workers is different than the general male population in the same age, right? So you know what the general population is. You want to know if construction workers have breathing issues because of their exposure to dust, right? So you sample. You don't have the resources to sample all construction workers, because if you could do that, you could just compare the two means, right? You wouldn't have to do any statistics, right? But you don't have the resources, so you can only sample 60 of them. 60 is a pretty big sample, right? So off the top of my head, I say, okay, now I know what the mean is for the population, but I have one sample I had to take for this construction worker. So I know a mean, and the other one I just know the sample. Okay, using pulmonary function, there's a data set that's in here that we're going to open up. It's an Excel file, and it's also as a SAV, a SPSS file. You want to test the hypothesis that is there a difference? So what would our null hypothesis be? Let's make a null hypothesis. What do you think would be a good null hypothesis? The mean? The mean, exactly, would be equal, always equal. Mean FEV for construction workers is equal to the mean for the general male population, right? What's our alternative hypothesis? They're different. Mean for the general population is different from the mean for the construction workers. So that's how we would construct this. So here we go. There's that one. And we always say mu, not X bar in the hypothesis statement, right? When we state our hypothesis, because that's really what we're interested in, the means. If we could find means for everything and not have to do statistics, it would be great, right? And they mean the alternative hypothesis is that they're not equal. Okay, using that data, based on a sample size of 63, what is the critical value of T that you would have to, I think there's a typo in there. Right? I said 60 over here, right? And I said 63 over here. Let's stick with 63 since they did that here. Okay? Based on the sample size 63, what's the critical value of T that you will need? I know why I did that. I meant to change them both to 60. We're going to see in a second why. Okay? But it's not critical. Okay? What is the critical value of T? It's not critical, and I'm talking about the critical value of T. It's pretty funny. So at any rate, what's the critical value of T for a sample size of 63? I get it from the table, right? So what t-value do I have to exceed? Okay, so I go down here, 95%, 5% chance of being wrong is a 95% confidence, same thing. Okay, I go down to 63. Well, we got a problem there. There's no 63, right? So we have to just kind of make a judgment. If we were looking for 70, right, I would say it's somewhere between 2.0 and 199. But you want to know something, they're so close, right, that, maybe I'd pick one or the other, or maybe I would pick, something in between, 1995, right, halfway between them. But in this case, I said 63, so maybe I'll just go with 60, 2.00. Okay. Now, had I known the population standard deviation, what would I have used for the critical value? Instead of the t-score, I would use the z-score. And what's the critical value for z when we want to reject the null hypothesis? 95% confidence. Alpha is equal to 0.05. What is that? That's equal to 1.96. That's why a lot of times, now I could use 2.0, but you want to know something? It's so close to 1.96. I might have said to myself, I'm not going to bother going to the table. The sample size of 60 is a pretty big sample. I'm just going to use 1.96. Okay, are you cheating when you do that? Yes. Like I used this analogy before, possibly, I'm not sure. It's like you're on the highway, right? What's the speed limit on the highway, right? Double nickel, 55, right? Does that mean everybody drives 55? No, that's the speed. The rule is 55. Sometimes you cheat a little bit, you go a little bit faster. It's kind of like that. The rule is if you don't know the population standard deviation, you use the z. If you don't know the population standard deviation, you have to use t. If you do know the population standard deviation, you can use the z-score, 1.96, as the critical value. However, when the sample size gets big, it's like there's no cops on the highway, right? You can go a little bit faster. You can go 60, right? So you know it's going to be, when the sample size is 60 or 70, you know it's going to be 1.99 or 2. It's going to be so close to 1.96. You might say, I'm not going to bother, right? Now, the software, SPSS, always uses the t-table. Even if the sample size is 900 and the t-score is 1.960001, it's still going to use that number instead of 1.96 because it can. It's just easy for it to use that number. For us, we have to go through an extra step in order to look up the critical value. So in this case, if I'm sticking to the law, then I'm going to use the critical value of t is 2.0. If I'm taking advantage of it's a big sample size, then I would say I'm going to use a z-score, call it 1.96. Right? On a homework like this, if you have a sample size that's over 50, 60, 70, 100 or something like that, I would probably make the acceptable range for the answer to be wide enough so that it would work for either one that you use. But if you got a small sample size like 25 or 10 or 16, you got to use a t-score. Okay, so let's take a look at this. Using the FEV data that's in that file, using SPSS, Excel, or R, calculate the value of t for the single sample t-test, right? X-bar construction workers versus other males. Enter a positive value for the calculated value of 1. It doesn't really matter if it's a positive or negative value because we're just comparing the size of the number, right? The size, the sign doesn't matter. The only reason we ask you to enter the positive value there is because in order for it to grade it correctly, it has to know. It won't know the answer to use either one. So that's the only reason you're being asked to put it in as a positive number. It may not really be a positive number. Okay, so let's open up that file. Let me see if I have it on here, so I don't have to go searching for it. What was the name of the file again? I'm going to go onto Blackboard and get it. Okay, I'm on Blackboard. Okay, and here it is. I'm going to save it on the desktop. That's the SPSS version, and this is the Excel version. I'm going to open the Excel version up first. Okay, there it is. Okay, here's the Excel version. Okay, okay, FEV1, that's all the different, that's the 60 workers, it's 60 workers. That's what the sample size turned out to be. Okay, so you can stick with 60 on there. Okay, so now I'm going to calculate X bar, right, for the sample, for the construction workers. X bar for construction workers. Okay, what is that equal to? It's equal to the average for all these numbers. Okay, I'm going to click on there and drag down. And I'm going to enter, and it turns out it's 2.831 liters. A little bit less than I would have expected, right? We were talking about normal population was 3. Let's see if that's a big enough difference for us to say that they're really different. Remember, that's only the sample. You know, we don't know what the population is. What else do I need? I need to know the standard deviation. Since I wasn't given the population standard deviation, I have to calculate standard deviation. I could type it in as S or SD, doesn't matter. It's just not sigma. So a standard deviation is equal to the standard deviation of all of these numbers. Okay, so there's the standard deviation. So now I have to determine what the standard error is, right? We know the sample size. I'm going to put sample size there first. We know the sample size is 60, right? Now I got to calculate the standard error, right? Standard error is going to be different depending on the sample size because it's equal to the standard deviation, sigma or the one from the sample, whichever one you have, divided by the square root of the sample size, square root of 60. Okay, so I'm doing this in Excel. You could do this with a simple calculator. Just easier and quicker for me to do this without making a mistake. So the standard error is 0.06, right? So now the question is this mean 2.81 far enough away? What was mu again? You guys remember? It was equal to 3.0, right? Right? Is that far? Are those two far enough apart for us to say, with less than 5% chance of being wrong, in other words, being 95% certain, that the true population, the mu for the construction workers, is different than mu for the population? Yes.
Just to be clear, whenever we're calculating standard error, we can use sample standard deviation.
Yeah, you really want it. The real rule is, what is standard error really equal to? Standard error is really equal to sigma, the true population standard deviation, over the square root of the sample size, right? That's really what it's equal to. But we don't have the population standard deviation, just like we don't have the population mean for construction workers. We don't have the population standard deviation, so we're stuck with an estimate for the sample standard deviation is an estimate of what the population standard, the estimate of the variability of the population as well. So we wind up using S instead, right? Like we did right there, or SD or whatever, whichever way you want to call it. Okay, so we have to use that instead. That means you got to use the t-test, unless it's a really big sample size, right? Arguably, you could argue 60 is a big sample size, but let's stick to the t-score right now. So now, are they far enough apart? So we got to calculate what t is. And what is t equal to? T is equal to the difference between the two means, X bar for construction workers, right, minus the mean for all workers, for all men in that age group, right, divided by the standard error, right? So what is t? So t is going to be equal to, well, let's do the top first. Oops. So what is t? T is going to be equal to, the top part of this fraction is the difference between these two means, which is equal to 2.831 minus 3, okay, which is negative 0.1691, 1.7 liters of air expelled, right? So that's what the top part is. The bottom part is the standard error. And what is that equal to? the standard error is equal to the standard deviation, that's that number, divided by the square root of the sample size. Okay, and what is the t-score equal to? The t-score is the top part divided by the bottom part. So t is equal to negative 0.169 divided by the standard error. Okay, so you do it step by step. And our t-score comes out to be negative 2.5. Now, what's our critical value of t? Right? What's the t-score that we have to? It's 2.0, right? It was 2.0. Now, if I really thought I had a really big sample, I could just say, instead of calling it t, I'm going to call it z, and the critical value is 1.96, right? Just as we use for 95% confidence interval. But since I want to be careful, I'm going to call it 2.00, right? So does the t value we calculated, the distance apart in standard errors for these two means, is it bigger than t critical? It is, right? So can we reject our null hypothesis? Yes. If it's bigger, if the distance between them is bigger than what we need to reject it, we reject it. So we reject the null hypothesis and we accept the alternative. So what have you just proved? You've proved with 95% certainty, less than 5% chance of being wrong, that there's a difference between the pulmonary capacity of construction workers who breathe a lot of dust and the normal male population in that same age group. Okay? And now you get you don't get a Nobel Prize. Maybe you get some sort of award from the American Industrial Hygiene Association or the American Public Health Association. I don't think it reaches the level of a Nobel Prize, but hey, that's something, right? Okay, so at any rate, so that's what we're after. That's where we're interested in proving this kind of stuff. Okay, so now the only thing here is that both of these situations we looked at now, we were dealing with a situation where there was a known mean, and we were comparing a different group, a different population, based on a sample from that population. A lot of the times, most of the time, in fact, we don't have a known mean. We have two groups, and the only thing we know about the two groups is each one of them has a different sample. We've got a sample of 100 people from here, sample of 97 people from here, and now we want to compare the two groups. So we don't know the true means. We know X bar for this group and X bar for this group, and we still calculate the t-score. We calculate t is equal to X bar 1 minus X bar 2 over the standard error, right? We calculate standard error the same way. We calculate the standard deviation divided by the square root of the sample size. The only thing that's a little sticky is now that we have two groups, you got a standard deviation for this group and a standard deviation for this group. Which one do you use? And what sample size should you use? Can you combine them, right? We're probably not going to get to that today, but on Sunday night, we're going to go through examples where now that we've done this, instead of working with one sample, we're working with two samples. Well, now what I can do is I can say to myself, gee, since I'm working with two samples, if the standard deviations of the two groups look similar, I'm going to combine them, and now I have a standard deviation that's more accurate, right? But if they're very different, well, now I can't combine them. I have to deal with them individually. So there's differences in the way you calculate the standard error. If you combine the two of them, if they're close together, you combine them. Or if they're different and you say that they're unequal, so I can't combine them, right? So there's differences in the formulas that you use to work them out. That was what we saw as we got towards the end of class. We went through all of those 3 pages. One for single sample t-test like we just did now, one for two sample t-tests with equal variances, where one is not double the other, and two sample t-tests for unequal variances, and then we started talking about paired samples as well. Okay, so now let's take a look at this using SPSS. I'm going to do exactly the same problem. I'm going to open SPSS. Remember, there was a second file there, right? It was the same data, right? But it's an SPSS file. Okay. So I'm going to say open data, stored on my desktop. So I'm going to go up to the desktop. Okay, there it is, pulmonary function data. Okay, there we go. There it comes. And you can see these are the same numbers. There should be 60 people here, 60 construction workers. So now I'm going to go into Analyze, Descriptive Statistics, and I'm going to say to myself, let's take a quick look at this, Explore. And I'm going to take that pulmonary function test, put it into the dependence list. There's only one sample, so there's nothing else to move into the factor list. And I'm going to ask it to give me some basic statistics. And it does. It tells me that the mean is 2.831. It's the same number we got. The standard deviation is 0.521. I think that's the same as we got. I don't remember anymore. Right? And right? Was it the same? I don't remember anymore, to be honest with you. It's the same. Good. Okay, good. That's reassuring, right? Okay, and the standard error is 0.067. Okay. Now remember, we might have rounded a little bit, so we might have gotten exactly the same thing. So now let me do the hypothesis test we just did, the t-test. And the way that I do that is I go to Analyze, I go to Compare Means. Hypothesis test, or with t-test, we're comparing means. And I will have a number of choices. A one sample t-test, independent sample t-test, that's two sample t-test, paired samples, and then some other stuff as well. So right now we're only interested in one sample t-test. I'm going to click on that. Okay, I'm going to move pulmonary function into the test variable that I want to work with. Okay, now what am I comparing the mean for the construction workers to? I'm comparing it to the known mean for the population. Anybody remember what that was? I think it was 3 liters, right? 3.0. 3.0. So I'm comparing it to the number 3.0, the known mean. Since it's a single sample t-test, we only have one sample, but we're comparing it to a known value for the other population, 3. That's why we have that test value down there. We can put any. If I had told you that the population was, the mean for the population was 2.9, you just put 2.9 in there instead. So I'm going to click OK, and it's going to do our t-test for us. Let's see what happens. Unfortunately, I can't blow this up easily, but I can read it to you. And the t-score is negative 2.50. What did we say the critical value was again? For that sample size, 2.0. So we exceed the critical value, so we can reject the null hypothesis. But look, if we keep moving across here, notice the degrees of freedom, 59. Sample size -1. Keep moving across here. See the significance here? This thing says significance. That's the same thing as what we call the p-value, or probability of being wrong, if we reject the null hypothesis. So that significance, or in other words, p-value, that p-value, right, it says two-tailed because remember our test, we said that they're either equal or they're not equal. We didn't predict whether one was at the lower tail or the higher tail, if it was bigger or lower. We just said different, right? So that's called a two-tailed test, right? So let's see, what's the probability that we would get these things that far apart when the null hypothesis was true? Well, the probability of the null hypothesis being true when they're that number of t-scores apart is about 1.5%, 0.015. Our chance of being wrong, if we reject the null hypothesis and it turns out to be true, the chances we're wrong is only 1.5%. What was our tolerable level of error? Alpha. It was equal to 5%. Since the probability of being wrong is less than the amount that we can tolerate, 5%, we reject the null hypothesis. So getting a t-score that's bigger than t-critical and getting a p-score or significance that's smaller than 0.05, same thing. They both mean you reject the null hypothesis. Okay? I see a lot of glazed eyes here, stuff like that. It's not that bad, right? I think if you go through this, do it on your own. Even if you have to do the same problem, there's 2 problems we just went through. Even if you have to do those 2 problems 3 times, and you get down what the sequence of steps is, right? It's like when you ride a bicycle, you don't think about staying up on a bicycle. It's called muscle memory, right? You just do it. You get so used that when you first get on it, it's not muscle memory. You have to learn, right? You see kids all the time. I just saw a guy in my neighborhood was running behind this kid in the driveway, right? Running behind this kid, as the kid was going down and wobbling away, and he's over there getting ready to grab the seat. If the kid's going to go over, kid doesn't know how to do it yet. But eventually the kid keeps doing it, and eventually he doesn't think about it anymore. He senses how to do it. Same thing here. If you do it often enough, it's not muscle memory, unless your brain's not a muscle particularly, but it is the same kind of thing. Once you get used to doing it, it'll make an impression. A light bulb will go off, and it'll be more intuitive to you as well. It'll be easier to understand. Okay, so all right, so let's call it a night on that. And then on Sunday, I'm going to go over the 2-sample t-test. Most of the time for the 2-sample t-test, I want to do one more thing before I just thought of one more thing I want to do before we break on this. The 2-sample t-test, most of the time you're going to be using SPSS because it's a relatively calculated calculation. Okay, so we'll talk about that on Sunday night. But in the meantime, I just want to show you one other thing, and that is this idea of a paired sample t-test. Okay, so let me see. Cornflakes, flakes. Let's see if I can't find it yet. Flakes versus Bran, that's it. SAV. Okay. I'm going to put that on desktop here. Okay, so I'm going to open up this other SPSS file. This won't take long. Okay, I'm going to open up. Okay, open data. Now it's called Flakes versus Bran. Open it up. And in this one, I have 2 sets of data. And you know how they're always talking about different kinds of cereal, lower cholesterol, and stuff like that. What we're looking at here is the amount of cholesterol. We had people eat oatmeal, cornflakes for a month, and measured their cholesterol before and after, and we saw how much it went down. Then we had them eat oat bran for a month, and saw how much their cholesterol went down, right? But the way we did it was we didn't get one group of people and say, okay, you eat cornflakes and we'll see how much it changes your cholesterol. And you eat cornflakes and we'll see how much it changes your cholesterol. We took the same person. And for a month you eat this stuff. Now for a month you eat this stuff. And we saw the effect of those on the same person. So now we want to know which was better. Which one of these was better at reducing cholesterol? Maybe this is the amount that it went down, right? Which one is better at reducing cholesterol? Okay, well, really, we're not interested in what their score was for cornflakes or oat bran. We're interested in what the difference was. Now, I'm going to subtract each one of these from the other, right? So 3.84 minus 4.61. The oat bran lowered the cholesterol a bit more. This one, it also oat bran. This one, it looked like the cornflakes lowered a bit more. Now, I'm going to get a column of numbers here, which is the difference between those two numbers. But it's for each one of those numbers is a difference for the same person. That's called a paired sample. Same person before. They took the placebo and they took the drug. A lot of times they don't know what order they took them in. They randomized the order they take them in, right? So you're going to wind up with one column, which is the differences. Now, if there's no difference between how much cornflakes and how much oat bran changes your cholesterol, what would you expect the average difference to be? 0. Exactly right. It should be 0. No difference. Sometimes this one will do it better. Sometimes this one will do it better. Sometimes so on and so forth. So the average difference you would expect to be 0, right? So instead of analyzing 2 samples, we just analyze the differences and compare it to 0 to see if it's different than 0. So what's our null hypothesis? Our null hypothesis is that the mean of the differences is equal to 0. Our alternative hypothesis, the mean of the differences is not equal to 0. And how do we analyze it? We go in here, analyze, compare means, paired samples t-test, and we move in these two. Notice it won't do the analysis unless you move in 2 variables each for the same person, and click OK. And it does a paired sample t-test, which is really a 1-sample t-test, but it's comparing it to 0. right? You don't have to put the 0 in there because it assumes that that's what you're going to do. And what did it find? It found out the mean difference was negative 0.36, but is that big enough in order to reject the null hypothesis? Well, the t-score is negative 3.34, and the degrees of freedom is 13. There were 14 people in the study, so degrees of freedom of 14 minus 1. And what was the probability? First of all, for 14, the critical value of t for 13 degrees of freedom is 2.161, 2.160. And if you look at our result, where'd it go? Which one is it here? If you look at our result, I'll go there and get the other window. If you look at our result, our t-score was negative 3.34, much bigger than 2 points, so we reject the null hypothesis. We can check also here. What's the significance, that p-value? 0.005. That's less than 5%. More evidence we can reject the null hypothesis. Remember, you want your t-score to be bigger than t-critical. You want your significance or your p-value, your probability of being wrong, to be less than 5%. Both of those basically always wind up going the same direction. Right? In other words, big t-score, small p-value. Okay? So that is the paired samples t-test is really another way to do a single sample t-test. Okay, so I'll get this recording up, and then like on Sunday night, we'll go over the paired sample t-test. I also put up the review that I did for our class, and also a lab that I did for a different class for 611. So you guys, if you're in BIOS 610 or BIOS 6 or PH 750, you can take a look at that video also. That's the lab from Monday night, for BIOS 611. Okay, so that's on Blackboard, on the announcements on Blackboard. You can play that, and it'll give you a preview of the paired sample that I'm going to go over on Sunday, if you don't want to wait until Sunday. Okay? Okay, good. Okay, let's call it a night. Okay, and you online, good work. I see a couple of right answers there. Okay, good. Oh, and we got some more people online too. Good, I'm glad to hear that.